So when a technical drawing is given to you, you should know how to give. You should know how to differentiate which one is the contour feature, which one is the center feature. The contour feature is also called the integral feature, and the center feature is also called the diameter feature. You can tell which part is the contour feature or center feature just by experience. Normally, the solid line in the technical drawing is just the contour feature, and the axis of the workpiece is, and the center point or the medium plane, just the feature is not really, when the feature is not really exist, and it's usually the axis, medium plane, they are the center features. They are the center features. In today's lesson, we are going to learn the geometrical tolerance zoom of the different geometrical characteristics. And we need to know what the tolerance zoom look like and know how to label it on the technical drawings. How to label, how to interpret the description of geometrical tolerance zoom and integrate it into the geometrical frame and label it on the drawing is the most important topic in this chapter. Okay, now let's continue our learning. And the geometrical tolerance restrain the actual tolerance, the features, and whereas geometrical tolerance are defined with their tolerance zoom. Using the tolerance zoom, we can control the actual features variation at a certain ranges. So first, I'd like to see when we are talking about the different features like a point, line, plane, how we constrain it, how to restrain these features. Let's first look at a point. If a point is in a plane, we can use a circle to restrain it, right? We can use a circle to restrain the point in a plane. If the point is in a space, we can use a sphere. It's a 3D sphere, and to constrain the point. So first is a point feature. Its tolerance zoom can be these two situations. If it is in one plane, you use a circle. If it is in the space, we use a sphere. So when the tolerance zoom is a circle, we need to put a phi before the tolerance value. We need to put a phi symbol. And if the tolerance zoom is a sphere, we need to put a s phi before the tolerance value. For example, if the tolerance value is 0.01 micrometer. And next, let's look at the line feature. When the feature is a line, what's the tolerance zoom may be like? If the line is in a plane, we can use two parallel straight lines to restrain the line where the line may lie. If we put a condition at here to restrain one direction of the line, then the line we can use two parallel plane to restrain the line. And if we restrain the direction in any direction, then the line can be restrained using a cylinder. When the tolerance zone is this shape, is a cylinder, remember we also need to put a phi here before we need to put a phi before the tolerance value. And if the line itself is a circle, then the tolerance zone is like this shape. It's a concentric circles. It's concentric circles. And if the line itself is a curve, we can use two parallel curves to constrain the tolerance zone. In the third condition, if the feature is a plane, if the plane is a straight plane, we use two parallel straight plane to constrain the plane. If the plane is the surface of a cylinder, then we use two coaxial, the space between two coaxial cylinders to constrain the cylindric surface. If the plane is a curved space, we just use two parallel curved surface to constrain the curved surface. So here is a quick look. Now let's look at different geometric characteristics. We will first learn the first type, the form tolerance. The form tolerance, here we can see there are four types. The first is a straightness. For straightness, the symbol is just a straight line. The flatness, we just use this plane symbol to represent flatness. For circularity, we use a circle as its symbol. For cylindricity, we use this symbol. It's a circle and two lines here. These are the symbols for these three characteristics. And when you see the characteristic, you need to remember what are the symbols like. And now let's continue the learning of form tolerance. The form tolerance items, it does not need the datum. From this table, we can see only the form tolerance does not need the datum. Other kinds of tolerance, profile tolerance, may use or may not use the datum. But orientation tolerance, location tolerance, and ran-out tolerance are all need the datum requirement. Do you still remember what the datum means? The datum for the tolerance frame, if the characteristic is the straightness, we may write down it. And just remember, it does not. If the characteristic here is these four kinds, straightness, flatness, circularity, cylindricity, then you don't need to put datum here. Because the form tolerance just describe its forms. It just describes its forms, and the form does not need the datum. So when we trying to label a fault tolerance, there are just two compartments in the tolerance frame. Here's what I mean just now. Let's see. Here is what's this characteristic I have just mentioned. straightness, yeah, correct. And then the tolerance value is 0.1. And here it points to the contour line of this cylinder, right? It points to the contour of the contour line of the cylinder. And here it also points to the contour line of the cylinder, and it says the characteristic is also straightness, but it has a phi here. So anyone can tell the difference. So first we need to know how to make the judgment to see the tolerance, the features. We first need to know in these two situations, what is the tolerance, the feature? What is the tolerance feature? So let's look at here. The first one, it points to the contour line. It points to the contour line. So here, the tolerance feature is this line, contour line, right? The contour line has the straightness requirement, and the tolerance value is 0.1. So what's the difference between this one and this one? You can see this is the lead line. The lead line is a line with this dimension line, right? So the tolerance feature is this contour line or not? No, right? Because you have said when the lead line is at the extension of the dimension line, it means that the tolerance feature is not the contour line here, but the axis here. So here, this label here, it means that the axial of the cylinder has the straightness requirement. Yeah, have the straightness requirement, and it requires that the axial is in a cylinder. It's in a cylinder, and the diameter of the cylinder is 0.1. Okay. So here's some summary for the fault tolerance. Except for the straightness, the flatness, circularity, and symmetricity features are always contour features. But and the straightness features may, here is the contour features, and here is the center features. The center features here is the axis of the cylinder. I hope you know what this means. Yeah, have you do you know the meaning? That means if it's a form tolerance, and it includes four kinds: straightness, flatness, circularity, and symmetricity. If it tells you it's the form tolerance, the characteristic is flatness, circularity, or symmetricity, then the lead line always point to contour features. It always point to contour features. But if it points to for straightness, it may have two conditions. It can be a contour line. It can be a contour feature. It can also be a central feature. So let's first learn the straightness. Straightness is a condition where all points are in a straight line. Yeah. In perfect condition, all the points should be in a straight line. And the tolerance, usually the tolerance zoom is limited by two parallel straight lines. And the distance of two straight lines is the tolerance value. It's the usually conditions. Here, let's look at example, and it's also on your book, page 19. Here, we should learn to know what the workpiece looks like. From these two views, you understand that it's just a cube, right? And on the right this part is cut off, and it's in here. So we know it says this. You should first tell if the tolerance the feature is a plane or a line here first. As we can see, the lead line points to this contour line. So this contour line, in fact, it is a plane, right? It's the upper plane. It's the upper plane of the workpiece. So how a plane can put a form tolerance as a straightness, because we say the straightness describes a line, right? So in fact, we need to use some. We use a way to get a line first. That is, we use a plane just parallel to the front view, and just use it to cut the upper plane of the workpiece. Then we can derive a line, right? Because the tolerance feature is the upper plane, and we need to get a line from the upper plane and restrain it by two parallel straight lines. That's how we get it. So this situation, the definition of the tolerance zoom is in the considered plane. The tolerance zoom, it is limited by two parallel straight lines, and their distance is t in the specified direction only. Here we can see this is the two parallel lines. Okay, this is the straightening, the first condition for the straightness, and also sometimes the tolerance zoom for the straightness is limited by a cylinder of a diameter t if the tolerance value is preceded by the sin phi. So here is the example for it here. Here's the example. The tolerance zoom is limited by a cylinder of the diameter t, phi t, and if the tolerance value is provided for the symbol, this symbol phi. So here is an example of indication and explanation, and we can see here. So as we can see, this lead line is the extension of the dimension line. So the tolerance feature is not the contour line here, but the axial of the cylinder, right? So the tolerance feature is the axial of the cylinder, and it has this kind of geometrical tolerance requirement. The characteristic is the straightness, and as you can see before the tolerance value, it has a sign here, the sin phi. It just means that the center feature of the cylinder is the axis, has the straightness requirement, and the tolerance zone is a cylinder with a diameter 0.08. So here is the example. So this is for the straightness. And here is a third example. So this example, as we can see here, it's just from the front view and the left view. You can see that it's just a cylinder, right? The cylinder, and the lead line point to the contour line. So it means that it has straightness requirement for this contour line. It has because it does not have a dimension line here. If here we put a dimension line, it means that the tolerance feature is the axis. So it has the straightness requirement for this contour line. And as we can see here, the tolerance value before the tolerance value it didn't have phi. So it means that the tolerance zone is two parallel plane and with a distance of t. So okay, this is for the straightness. Next, let's see the flatness. Flatness, it means that all the points on a surface are in one plane. So ideally, all the points should be in one plane. And what is the tolerance zone like? So the tolerance zone will be specified by the zone formed by two parallel planes. We use the two parallel plane to constrain the tolerance plane. And the tolerance value is the distance between the two parallel planes. All the points on the actual surface should be between the two parallel planes. As you can see, here is the example. The lead line point to the contour line here. This contour line means it's the upper plane of the workpiece. So it has a flatness for the upper. It has a flatness requirement for the upper plane. It also means that the upper plane can be constrained with two parallel space, and the distance between these two parallel spaces is 0.1. So this is the flatness. I think it can be easily understand. And the next is the circularity. We describe orientation. Usually, you must already familiar with the parallelism, right? Parallelism. When we say parallelism, we can describe normally if in one plane we usually describe two lines parallel to each other. But in space, the feature can also be plane. So we can have four kind of situation. A line can be parallel to another line, right? And a line can parallel to another plane. And also two planes can parallel to each other. And the plane can parallel to another line. So there will be four situations. And it means the datum. So here we can introduce a bit about the datum in orientation. So when we say one line parallel to another line, so the other line is the datum, right? It's easy to understand. And also we have the characteristic perpendicularity. And the symbol you must already familiar with. So for perpendicularity, it also has the full situation, right? Because the tolerance, the feature can be a line and also can be a plane, and the datum can also be a line and can also be a plane. And the third characteristic is angularity. If the two features is not parallel and not the perpendicularity, they can have certain angle requirement. They have certain angular requirement. They is the angularity. So now let's move on to see in details. There are altogether three kinds of orientation tolerance: the parallelism, the perpendicularity, and the angularity. The tolerance features can be a line or a plane, and the datum features can also be a line or a plane. So for each one of them, there will be four situations. The tolerance zoom between two parallel planes. The tolerance zoom is always between two parallel planes or within a cylinder surface. It should be noted that the tolerance zoom must follow the specified orientation to the datum features. When the tolerance zoom is the space within a cylinder, the tolerance value must be preceded by the symbol phi. So let's first look at the parallelism. It is the condition of a surface or axis parallel to a datum plane or axis. So we can change the tolerance feature. When the tolerance feature is plane, the datum feature can be plane, and it can also be a line. When the tolerance feature is a line, the datum feature can be a plane, it can also be a line. Let's first look at the first situation. It's the plane parallel to another plane. Here, the later plane here is the datum. This is the datum plane. The tolerance zoom is the space between two parallel planes, and the two planes must be parallel to the datum line as well. Here is wrong. It should be datum plane. Here it should be the datum plane. And the tolerance value is the distance of the two planes. Here is the example. This workpiece has this parallelism requirement, and let's see how it's labeled. And as we can see, for angular tolerance, it's always need the datum. So we want the upper plane parallel to the lower plane here. So here, this plane to this plane. So this plane is the datum, right? We need to put the datum here. So how we label the datum? We can use this symbol. You can but that's the old standard. I want to use this symbol here. It's the A. You can write down like this here. You can also write down like this here. It's the D. So here is the label of the data, and we want to say this plane is parallel to this plane. So the lead line just point to the contour line of the upper plane. This contour line represents the upper surface. So the lead line just point to it. Remember, this is perpendicular. This is perpendicular, and this is the characteristic symbol. It's the parallel, and the tolerance zoom is the space between two parallel space. So there's no phi. Just write down the tolerance value here. is the 0.01. And different from the phone tolerance, the orientation tolerance always need the datum. And here is the datum, here is the datum, and we need to put the D here, put the D here. So here is an example of a plane parallel to another plane. Now let's look at the second situation. That is the tolerance, the line to the datum plane. And the tolerance zone is the space between two parallel. The line is between two parallel planes, and the two planes must be parallel to the datum line as well. The line should be changed to plane here. Must be parallel to the datum plane as well, because here is the datum is the plane. As we can see here, this is the parallel space to restrain the tolerance line. And these two planes should be parallel to the datum plane. Should be parallel to the datum plane. So let's see an example. In this example, from these two views, we can know that it's a cube and there is a hole here. That's a hole here. And the datum here is the B. The B, as we can see, it's the lower plane of the workpiece. It's the lower plane of the piece. So this is the datum plane. You can interpret this plane to here. And we can see here, it has the parallel requirement, parallelism requirement, and this is the symbol, and this is the tolerance value. The tolerance value 0.01 represents the distance between these two parallel space, and the datum is B. Here you need to know what is the tolerance feature here. What is the tolerance? As we can say, it says 9 to the tolerance 9 to datum plane. The datum plane is clearly here, is the lower plane. So what is the tolerance 9? The tolerance 9 is which line? Because the lead line is at the extension of the dimension line. So here the tolerance feature is this the axis of the whole. It's the axis of the whole. So it's just this geometrical tolerance is try to restrain the axis of the cylinder. Want to restrict it in two parallel planes, and these two parallel planes should parallel to the datum plane. Here is the second situation. The tolerance line to datum plane. Now let's see the third situation. That is the tolerance plane parallel to a datum line. The tolerance zone here is the space between two parallel planes, and the two planes must be parallel to the datum line. These two parallel planes should parallel to the datum line. And let's see this example. So this is the, as we can see, this is the tolerance plane, right? And the datum line is here, indicated by the datum symbol here. So can you tell which is the datum plane and which one is the tolerance plane and which one is the datum line here? Let's first look at the datum here. So the datum is put in here. So is the datum this contour line is the datum? Yes or no? No. Why? Because this datum is at the extension of the dimension line. So it means that the datum is the central feature, right? the center feature here is the axis of the hole, right? So the datum line here should be the axis of the hole, That's the datum, and this axis is the datum line here. And tolerance plane, as we can see, it indicated by here. The middle line point to the contour line of the plane. Because as we can see, it's a concentric cylinder, and here it uses a plane to cut it off, right? Use a plane here to cut it off. So the middle line points to this contour line. This contour line represents a plane here. It represents a rectangular plane. It represents the upper plane. And this plane has the parallelism requirement. And ideally it's a plane here, but because the geometrical error, and we need to use two parallel planes to constrain. And the two parallel space, the distance is t, and it equals 0.21. So this is the third situation. And in the end, let's see the line parallel to line. So the line parallel line may be specified one direction or any direction. Here we give two examples. It's specified in one direction. When a line parallel a line is specified one direction, the lead arrow must perpendicular to the direction. Here are two examples that has the parallelism requirement. The tolerance feature is a line, and the datum is also a line. Let's first see this example. And as we can see here, we should first know what is the datum feature and what is the tolerance feature. As we can see here, the tolerance feature is at the extension of the dimension line, and for the datum, it is also at the extension of the dimension line. So here, the datum feature is the axial. I think the axial is here. It's the axis. It's the axis of the hole. And here, the tolerance feature is the axis of the hole. So this axis should be parallel to this axis, and the tolerance value is 0.2. So how the tolerance zoom should be looked at? So first we got the datum line here. It's represented by here. This is the datum line, and the tolerance space. The tolerance zoom should be two parallel plane. These two plane is parallel to this datum line, and the space between it should be equal to 0.2. And as we can see, the tolerance zoom, the two parallel plane has one direction restriction, because it is, as we can see here, it should be in this direction. And by contrast, we see the lower example, so the second example. We just change a little bit how we label it. The tolerance feature is not changed, and the datum feature is not changed, but we just change it when we label it. We just change the direction from this direction to this direction, from this direction to this direction. Then the tolerance zoom, the plane should be shift by 19 degrees. So the tolerance, the data line is still this line, but the tolerance feature should also be in two parallel planes. But this two parallel plane just changes direction by 19 degrees. So let's see the third example. Just when we label it, if before the tolerance value we put a 5 here, then it means that the tolerance zone is a cylinder. The tolerance zone is the space within the cylinder, and the tolerance value is the diameter of the cylinder. So here, and as you can see, this is the data line still here, and the cylinder is here. The axis of the cylinder is parallel to the data line. The axis of the cylinder should be parallel to the data line. So if the line is restricted in any direction, like this, then a phi symbol should be put before the tolerance value, because the tolerance zone is a cylinder. So now let's move on to the location tolerance. Location tolerance has three types. The first is the position. The second is concentricity or causality. And the third one is symmetry. There are three types of location tolerance. First, let's look at the causality. It means the axis of all cross-section elements of surface of revolution are common to the axis of the datum feature. Causality tolerance specifies a cylindricity tolerance zone where axis coincides with the datum axis. The tolerance value is the diameter of the cylinder. Here is the example. So here we got two data. Here, the data A means the axis of this cylinder, the left cylinder, and the data B means the axis of the phi D2 cylinder. And the tolerance feature, as we can see, these are aligned. So the tolerance feature here is this axis. This axis has the causality requirement, and the tolerance zone, is like this one. Here is it's a cylinder, and the diameter is the 0.1. And here is the common datum A and B. And A and B, ideally they should be in the same axis right here. So they can be used, here they serve as the common datum here. You use A and this. How do you say this in English? Maybe not minus, because here it does the mean minus. It does it means slash, right? Slash B. Okay. It's here. It's the common data. It's the common data.
A to B.
Yeah.
A to B. Yeah.
A to B. Okay. Okay. That's the causality. Now let's see the second one, the symmetry. And symmetry. Here we just use the example to explain symmetry. The slot here, it requires symmetry with the median plane. So the median plane is the datum plane. The datum plane, how to get the datum plane? Datum plane is indicated by this. As we can see, the datum A is at the extension of the dimension I. So the datum plane is the median plane of the all workpiece. Is the median plane of the all workpiece, and the slot here, as we can see, the tolerance feature is the median plane. It's the median plane of the slot. It's the median plane of the slot. Because the midline is aligned with the dimension line. So the tolerance feature here is not. It is the tolerance feature. Originally, we can think is you can get it from the real surface of these two surfaces, but the tolerance feature is the median plane of the slot, and the datum feature. Datum is the median plane of the workpiece, of the all workpiece. And here is the dimension line. The dimension is the tolerance zoom. The tolerance zoom is the space between two parallel planes. And here, as we can see, the plane A, in fact, is corresponding to the datum here. Is the median plane of the workpiece. So this plane A is fixed, just fixed. And then we try to find the two parallel space equally. They have the same distance to. They have these two parallel plane should have the same distance to the datum plane A. So the tolerance and the total value is the distance between the two planes of the tolerance zoom. So if the tolerance value here is the 0.8, it means that the distance from these two parallel planes to the datum plane A is equal to half of it. Okay. And then let's see the position tolerance. So when we talk about a position in space, we normally use x, y, z, the coordinates to describe its position, right? So here, when we are talking about the position tolerance, we also need to set up the dimensions. So normally, when we try to locate a position in space, it will need three datums in three different directions: the length, the width, and the height. So, for example, for workpiece here, it has three holes. As we can see, it has three holes. So, the axis of these four holes should normally will have the position tolerance, because these holes usually used to fit with another shaft. So its position must be correct, right? So its position will have the position tolerance. And here's a new concept. is called the theoretical exact dimensions. We'll see what it means later. And from its direct meaning, we can learn roughly what it means. Theoretical exact dimensions. So when we try to locate the location, we need to establish the Datum system, and for a space location, we usually need three datum. We usually need three datums. There are primary datum, secondary datum, and the third datum. As here, we can see two workpieces. In fact, from technical drawing, they are almost the same. But they are slightly different. This view, they are exactly the same. But from this view, can you see any difference? Can you see any difference? Yeah. Here, AB, and then this BA. So let's see what is. So when the first datum here is called the primary datum, and the second here is the secondary. There is here it didn't put a third datum. So when we set the position tolerance, we should first use the primary datum. Let's see the first datum here. It's the A. What did the A mean? The A mean is the lower plane of the cylinder. It's this plane, right? This plane. So when this workpiece fit with the other workpieces, we should first make the primary datum fit it to put it in its position, as we can see here. The primary datum is just at its exact position, right? But as we can see here, the datum B here is at the extension of the dimension line, right? So the datum B is the axis of this cylinder. It's the axis of the cylinder. So when we put it together, we first try to meet the requirement of primary datum. This plane is fit well, but as we can see, the axis does not fit well now. So this is the primary datum, the difference where we put the A here or here. So now let's check here. And here, the datum B is the primary datum. So we first need to try to put the axis align with the axis of the hole. Then we will see this plane, the lower lane, also the secondary datum does not fit well with this plane now. So this is the datum system, and when we put the order of the datum will affect how it fits.
So what is M?
M is it's called the Geometrical Tolerance symbol. We will introduce it a bit later, and when the tolerance value got a symbol like this, a circle and a letter here, it means that when we try to manufacture it, we need to not only consider this value here, but also need to consider its dimension error we learned in the last chapter, because dimensional tolerance and the geometrical tolerance, in some cases they will interfere with each other. So we need some kind of principle to deal with the situations. And M means the maximum material principle. But in most cases, we just don't have to use these principles. In 19% cases, we do not have to consider the interaction between the dimensional tolerance and the geometrical tolerance. Okay, but we'll introduce it later. Later. On the technical drawing, the theoretical exact dimensions is enclosed in a box. For example, here, these are the TDEs. And the tolerance zoom position must at the theoretical position. The tolerance zoom position must be at the theoretical position. For example, here you have a position tolerance. This is the characteristic symbol, and it got a phi t. Phi t means that the tolerance zoom is a cylinder, and the tolerance value is t, and the data is a. The data is a. So, in fact, for these workpieces, if we want to locate the axis of these holes, locate the position of these holes, we will need at least two datums. That is in the length direction and another one in the y direction, right? It's just, in fact, it should be put here. It's better. And here, the tolerance feature is first you should know the tolerance feature. The tolerance feature is the axis. It's the axis of these six holes. And it has 6 multiplied right down here. It means that it has 6 holes. It means we have 6 tolerance features, and they all the axes have the same position requirement, and their axes should be in the exact position. This position is determined by these values. These 3 values determines the position of the axis, and the axis, the position arrow of the axis should be within a cylinder. The cylinder, the diameter of the cylinder is phi t. This is the theoretical exact dimension. So now let's look at another example. It's the position tolerance of a point. Here, look at this workpiece. It has a position tolerance for the center point of this sphere. And let's see. So when the tolerance feature is a point, and it's for its position, the point position is in the space. So the tolerance zoom will be a sphere, right? So the tolerance zoom is limited by a sphere of a diameter t, and the center of which in the theoretical exact position of the considered points. As we can see, it has swing datums. The datum V helps set up the datum for height, set up the reference for height, and this set up for the reference for the y's, and this for the this for the length, this and A, the Datum A set a reference for the y's, So by these two theoretical exact dimensions, we can help locate an exact point in the space. But in fact, it has some sort of errors, and it is help we use a sphere to restrain the center point of the sphere. And here is how we label it. This is the position characteristic symbol, and this is the tolerance shape. We use S phi. It means that the tolerance zoom is a sphere, and the diameter of the sphere is 0.3, and the three datums are ABC. The ABC helps establish three-dimensional coordinates. And this is the position tolerance of a point. Now let's see the position tolerance of a line here. The tolerance zoom is limited by a cylinder of a diameter t, and the axis of which is in the theoretical position. Before the tolerance value number, there must be a phi. So let's see the example here. This workpiece, we want to set a position tolerance for the axis of this hole. So we first set up the three-dimensional Datum system. The Datum A is for the reference of y's, and the Datum B for the reference of height, and the Datum C for the reference of the length. To locate the axis, we need two theoretical exact dimensions. These two, as we can see, they put a rectangle here. The exact values are omitted, and this is how we label it. And it has the characteristic symbol for positional tolerance, and the tolerance zoom is a cylinder. So we put a phi here, and this is the tolerance value, and this is the three datums. So this is for the positional tolerance. And how about we have a 10 minutes break? Method is closely related with the measurement, and it can also be controlled by tolerance zoom. There are two types of layout. First one is a circular layout, and the second one is a total layout. And for circular layout, it can have two directions. The first one is in radial direction. The circular layout provides control of the circular elements of a surface, and the tolerance is applied independently at any circular measuring position as the part is rotated 316 degrees. Just here is an example. We try to measure the circular layout in the radial direction, and this is the characteristic symbol. This is the tolerance value, and this is the datum. The datum is the common axis, the common datum of datum A and datum B. It means this axis and this axis. And the tolerance feature is how we get the layout arrow. You just put a micrometer here and rotate. We normally use a 2V block to support this end and this end, and rotate it one circle, and the micrometer the value on the micrometer will change. And we just use the maximum value to minus the minimum value and to get the circular runout. And the circular runout value arrow should be less than the tolerance value, So here is the explanation of the tolerance zoom, The measured value, in fact, is it can be seen as a circle, and we use two concentric circles to restrain it, and here is the tolerance zoom. A circular runout tolerance applied to surface constructed around the datum axis controls cumulative variation of circularity and causality. It means that the measured value includes both the circularity and the causality. And in fact, the measured arrow, if you measure the circularity here, get a circularity arrow. And you can also measure the causality value here to get the causality arrow. The circular runout arrow must be larger than the corresponding circularity and the causality. When applied to the surfaces constructed at the right angles to the datum axis, it controls circular elements of a plane surface. This is the circular runout in radial direction. And the circular runout can also be measured in the axial direction. That is, for example, in axial direction, we do not put the micrometer in this direction, but put it here. Then the tolerance zoom is limited at any radial position by two circles at distance t apart, lying in a cylinder of measurement, the axis of which coincides with the datum axis. When measure it, as we see here, this is we use two concentric circles, but for the circular runout in axial directions, maybe in your book it can be more clearly seen, as you can see on page 105. The first example in this page. When you measure the circular runout in axial direction, the tolerance zoom is you can see more clearly on the book. The tolerance D, the two planes, the right planes. This plane, between this plane, their distance. Their distance is the tolerance value. This is for the circular runout in axial direction. For total runout, it also has two directions, the radial and the axial direction. For radial direction, the tolerance zoom is limited by two co-axial cylinders at a distance t apart, the axis of which coincides with the datum axis. In fact, it's just a little bit different from the circle runout in radial direction. When we use the micrometer to measure it, the circular runout here, we need to keep moving it in the axial direction. So when we measure the total runout arrow, the measured arrow value will be larger than the circular runout. So because when we move, it gets will get the largest value when the moving and get the smallest value here. And this is for the total layout video. And later I will show you a short video to give you more direct impression how we get the total how we get the layout arrows. And the total layout also can be measured in axial direction. The tolerance zoom is limited by two parallel planes and the distance t. The distance t is the tolerance value, and it's perpendicular to the Datum axis. It's perpendicular to. We just change the symbol, but it has different meaning. It means that the micrometer here just keep moving up and down, so it can get a larger value, larger layout arrows. It keeps moving, so then it can get the largest value and the least value. So here, let's see a short video. Then it will help you understand it better. So in Chinese. This is the micrometer. So this is two V blocks. These two V blocks. It's just a brief introduction, and I will still not go to details. Firstly, is the circular layout in the radial direction. Let's see. This is the data, and we use the micrometer to measure the layout. This is the common data. So this is how we measure the layout arrow. We use two blocks. These two blocks, in fact, is help to set up the the common datum A and the common datum B, and then we rotate the workpiece in one circle, and the indicated value here will fluctuating. You get the maximum value and get the least value, and the difference between them is the layout arrow. Normally, we will measure the layout arrow at a different place here, and the maximum value is used as the final results. This is a different way to set the data. Here, the data is set up by these two places. We measure different layout arrows at the different places, and the largest one is the final result. Is used as the. Then is the layout arrow in axial direction. This is the data. This axis is the data, and we try to measure the layout, circular layout of this plane. So we also use a V block to help get the data here, and then the micrometer point to the surface of the tolerance plane, and we rotate it. And if it has a layout arrow in axial direction, it will move in this direction. That's the layout arrow in axial direction. And as we can see, the value will fluctuate. We get the maximum value and the least value minus the difference, then is the final results. And here is an example. We set a different way to get the datum change. This is to get the datum aligned with the labeled one. And this is a different way to measure the circular route in axial direction. Okay. So I hope this video help you understand this meaning, because circular route is closely related with the measurement, and here is the just after we see we use two V blocks and rotate the block piece, and the value indicated on the micrometer will fluctuating, and we need to the fluctuate the maximum minus the minimum, the value, the radial, so the circular route error should less than the tolerance value. This is the first example showing the video, and the second one showing the video that we use the micrometer to measure the fluctuation of this plane when it rotates, and it will move in this direction, and this value is the circular route in axial direction. And the total route, in fact, is when you measure it, you just keep moving it, also moving the micrometer, then you can get a larger route value, and this is called the total route, and this is in radial direction, and this is for the axial direction. So, besides the profile tolerance, we have introduced the most of the geometrical tolerance already, and as we have said, sometimes after the tolerance value we got the N, L, some symbol like this. This is because when we dealing with the dimensional tolerance and the geometric tolerance, sometimes they will interact with each other, and we need some ways to deal with it. In fact, in most cases, we don't have to pay attention to their interaction, because most
cases they are independent to each other. The dimensional tolerance is independent with the geometrical tolerance. So most cases just use the independency principle. But in some cases, we will use mutual dependency principle. For example, the envelope requirement. If it's an envelope requirement, the value will be followed by letter E, and the maximum material requirement, N, and least material requirement, and reciprocity requirement. And the tolerance principle, you can refer to these two ISO standards. I will not go details into this, but you should know there exists such a thing. When you design it, most cases you can just use the independent principle. So here is a little summary for today's lesson. When the tolerance feature is an axis, most of the time, the tolerance zone is most of the time the tolerance zoom is within the space of the cylinder, and the phi should be preceded the tolerance value. And the second, the tolerance feature and the datum features are always axes for causality. The tolerance feature of ran out is always control feature, and the datum features must have axes. Sometimes has counter features. The tolerance feature of flatness, circularity, symmetricity, profile of any line and the profile of any surface are always counter features. These are always counter features. So let's have a little practice. This question is also on your book on page 113.4. It's the 4-3. That is the first the question A. Question A. Try to find out and correct mistakes on this. I will use the blackboard to. First, I'd like you try to find the errors and correct them. If you do not know how to correct it, you can turn to page 19 to 102. This gives all the details of the geometrical tolerance, and you can try to find the errors on the labeling. As I have said, the labeling of the geometrical tolerance will be the most important part in this chapter. So I will first draw the technical drawing. So as I have said, the form tolerance does not need a datum, right? If, as you can see, it's a circularity. That means all the points should be in a circle. So it does not need a datum. You can think about it. It does not need a datum, and what's the problem with this book? It put a datum there, right? So it does not need a datum there. It does not have any relationship with another features. That it does. When we describe this, it means that when you use for this cylinder, you use a plane to intersect with it. You get a circle. It has a circularity requirement, and the value, and the tolerance zoom is two concentric circles, right? So you don't have to put a phi here. So that's the end of it for the circularity here. So let's move on to the next one. It's got two circles. What it means? Causality, right? Causality. And for this, it has anything wrong? You should, if you want to find the correct answer, you need to find the causality in the book. You look at the tables to try to find if anything is wrong. Like you can turn to the page 101. And you can look at this example here. This example. And to see, hey, anything wrong with this? In fact, it has it needs datum, right? So you need to check if the datum has been put there correctly. The datum is the A, common datum A and B, right? And the datum A and the datum B are the axes of this cylinder and this cylinder, right? So we need to put the datum at the correct position also. So on the book, the A is put here. Is it correct?
Yeah. A.
A on the book it's here.
Yeah, yes.
It's here.
Yes.
Is it correct?
Yeah.
You think it's correct? I don't think it's correct. Because if you put it here, it means the datum is the surface of the cylinder. But we want the datum is the axis of the cylinder. So we need to change it.
Put on.
The datum A should be put at the extension of the dimension line here. Here I will use the new standard equation here, and then this is the datum A. This is the correct way. Okay, remember? So only in this way you are indicating that the datum is this axis, not the surface of the cylinder, not the surface. Because you can imagine that when the datum is associated with the cylinder, it's always at the extension of the dimension line. Why? Because you can think about it. If the datum is the surface of a cylinder, how can it be used as a datum? It will be very difficult to use as a datum. So this is here, and this here is also the same, right? Yeah, you got to put them together here.
Yes.
And this is the B, right?
Yeah.
So you need to correct the name on your book too. Okay. So we move the B from here to here.
Yes.
So it's just indicate that this is the datum is this axis. So we get the common datum now. Now we're going to go back to the causality characteristic, and the symbol of course is correct, right? And here it got a phi here. For causality, so you need to know the tolerance feature. The tolerance feature is the center feature or contour feature. Is the contour feature or the center feature?
Yes.
Has to be a center. Because
Causality is the center feature, right? So when the lead line should align with this dimension line, right?
Yeah.
So it got something wrong.
yes.
Yeah. You need to put the lead line just align with the dimension line. So in this way, it means that the tolerance feature is this axis. This axis has a causality requirement, and the datum is this the common datum here. Is two datum. Okay. And try to see in the tolerance frame, is there anything wrong? This is the characteristic symbol. So the value,
Diameter.
it needs to increase diameter, because the tolerance zone is a cylinder, right?
Yeah.
The tolerance zone is always a cylinder. And the datum here is the common datum. Is the common datum. Okay. 2 problems solved. Let's move on.
3 problems.
4.
4 problems.
Yeah. I mean, these two label associated problems are solved. Now, let's move on. There are only 2 remaining labeling. So let's look at the.
I have a little question.
Yeah.
0.01. Don't need to A. The first one.
Yeah.
You don't need to A.
That's the problem with it.
Yes.
Because it's a form tolerance. For form tolerance, it does not relocate datum. As when you look into the form tolerance, it's the circular, straightness, flatness, and symmetricity.
Whose example?
Page 80.
Whose example? 0.01 here.
Here. For form tolerance, this straightness, flatness, circularity, and symmetricity, they all do not
Don't
need
need
data. Yeah.
Understand.
Because it's just described, it's if it's a circle, it's an ideal circle. The part, it's a, okay. So now let's look at the third one. Is there anything problem with the symmetricity? Is there any problem? The symmetricity. The symmetricity in the book is just a point to the here, right? It's a point to here. You look at it. So, what it means? The cylindricity, the tolerance feature must be a cylinder first, right? If the lead line aligned with the dimension line, what it means? It means the tolerance feature is what? It's the axis, right? It's the axis. So the axis can have a cylinder requirement. Can it possible? It's just a line. A line cannot have the cylindricity requirement, right? So it needs to point to the cylinder. It needs to point to the cylinder. So the labeling itself is correct. There's no problem. I mean the information in the tolerance frame is correct. The value is and it also does not need a phi. It does not need a phi because it's the space between two spheres or two cylinders. But the pointing line here, you need to change. You need to change it pointing to the. You can point it to the. You can point it to the contour line of the cylinder here. You can also point to here, but just do not align with the dimension line. If you align with the dimension line, it means that the tolerance feature is the axis, not the cylinder. Okay? Okay. Most of our problems are solved. So the final one, what does it have any problem?
I think the figures. Could it be the figures?
The last one is the total layout, right? So the total layout, if you are not sure what's the problem with it, you can look at the related illustration. The related illustration is on page. On page, I think it's on page 105. Its total layout name is on page 106. Yeah. Can you see any problem with it? I think it has two mistakes, in fact.
Okay.
First, you can see the lead line is at the extension of the cylinder, right? So, but when we use the total layout, the tolerance feature must be a contour, right? Must be contour. It cannot be the axis. So it needs to be put here. The target is here. You should not put it aligned with the dimension. And the next, what about the tolerance frame? Has it got any problems?
No, in the data.
You didn't find any problem? 0.3, it's okay. Value is okay. How about the datum?
A to B.
The datum, in this case, as we said, the layout is always associated with the measurement. In this case, the datum should normally will not be datum A alone. It will be the common datum A minus B. Okay. Okay. So that's the correction of geometrical labeling, and you need to.
Yeah.
I-
What
yeah.
about the
Yeah, you find the mistakes.
what about this?
Yeah.
How come this trinity is
Yeah, you don't have to go to that details. It's just give the. Here we do not focus on the real
Okay.
dimension of these two values.
okay?
Of course,
So for the function, that will be the part that we explain about the function.
Yeah.
Example.
This one, I
The one
forgot.
that is due A. The one that we put A inside the
Here.
would be
Ah, the one that is here.
Yeah, this one.
You got to
because
point to the
it says this
counter
one
line
is
or the
inside
extension of the
this
counter line, but
one.
just do not
Inside
align with the dimension line. If you align with the dimension line, it means that the tolerance feature is the axis.
This like this.
Yeah.
No, not this one.
Yeah. Yeah.
Okay.
You know,
And
this one we can refer to the
and this one.
take the
So it's at the end of these tables. Yeah.
Here, this one.
Yeah. As you can see, you cannot point to the dimension line. If you align with the dimension line, then yeah, it has to point to the counter line and the, yeah, and the common and the common data. Yeah. Okay. So I will give you
They run out. Can you please explain it once again?
run out. Okay. The run out has two mistakes. The first, on your book, the midline is at this place, is at the extension. So if we, the total run out, normally, there are two cases. The first case is the total run out of the cylinder surface. Another one can be the plane, this plane or this plane, the plane of the cylinder. This plane or this plane can be measured. So first mistake is that if the lead arrow, the lead line is here, it means that the tolerance feature is the axis. One axis, the axis cannot have the total run out. It cannot have run out tolerance. It cannot have tolerance. So we just change it from here. And the next, this is the tolerance value because the tolerance zoom is two coaxial cylinder, the space between two coaxial cylinders. So it's not a cylinder, so you don't have to put a phi here, and just this is okay. And then is the datum. Originally, it's just use one datum A, but as we have said, the run out tolerance is always associated with the measurement. So in these cases, when we try to measure the total run out, we need to use datums. We need to use the V blocks to support it. Let me see. So how we support it? We just use two V blocks to support it. They form the common datum. That is the A/B. You can look at the page 106. 106. It shows the first example is the total route in radial direction. Or here, here you can think about it. We want to measure the total random out here. Then, as I have shown in the video, we got to use a V block to support the workpiece. If we do not use, we can use A minus B, or we can just use the B. You can use a V to support it from on this side. But in most cases, we just use two blocks. But A alone, because we still need to do the test here. So in this case, we need. When I play the video, have you seen it?
Yes.
Yeah. We need to use the C block to support the workpiece, right? But here we want to measure the total layout of this cylinder. Then the data cannot be here. The V block cannot put it here, because when we do the measurement, the V block will put here and the V block put here. Then we use the micrometer pointed here and rotate it and try to measure it. Okay, so it should be A minus B. In this way, the workpiece is hold stable, and we rotate it and use this micrometer to measure the fluctuation.
So, Roshi,
Yeah.
we are